Hey, hi everyone. Welcome back to the Topos Institute Colloquium. Today we are pleased and honored to have Susan Niefield from Union College. She retired from Union College, and today she will be speaking to us about Cauchy completeness and adjoints in double categories. So Susan, whenever you are ready.
Okay, thank you for the invitation. And let me start by just saying why I'm interested in this or what led to this particular talk. Oops. It's not advancing.
Oh, do you want to try exiting
Right.
from full screen and seeing if?
There it goes.
Oh,
Okay.
there, great. Yes, thanks.
And I'm just, sorry about that. This is going to be in the way. Now it's gone completely.
Yeah, it looks great.
Is that blocking it?
No,
There.
nothing is blocking it. I just see your full screen.
Yeah, I pushed something because my space bar wasn't advancing it, and then things changed. Okay, so first of all, Cauchy completeness for categories, for bicategories, was introduced by Bill Lawvere in the early 70s. And he had a paper which is actually now one of the first TAC reprint, but in any case, he defined Cauchy completeness for metric spaces by considering a metric space as a category enriched in the monoidal category. That's the extended reals, extended non-negative reals, with the monoidal structure is plus and 0, and the Ham structure is truncated subtraction. And people refer to them as Lawvere metric spaces or generalized metric spaces because they're missing one of the axioms, but everything he did would work if you add the axiom. Okay. It's not advancing again.
How about the arrow keys? Do you think the arrow
I
keys are...
tried. Yeah.
No? Okay. I'm sorry about that.
Yeah, it worked before, but I don't know, it went back.
Yeah, it worked before when we were testing it earlier.
Yeah. There we go. There we go. Okay. Okay, very recently, Bob Paré introduced or discussed Cauchy completeness in double categories, and I'll explain what the connection is later. But he showed that an SR bimodule M has a left adjoint in a double category of commutative rings if and only if it's that should say, sorry, is a left adjoint if and only if it's finitely generating projective over S. It should say either has a right adjoint or is a left adjoint. Okay. Now that condition, finitely generating projective, is well known to be a condition for tensoring with, and I'll say S module, S is commutative ring, to have a left adjoint. And in a 2017 paper with Wood, we went through a general proof that had not just commutative rings for tensoring having a left adjoint, but commutative rings, and commutative quantales from the same theorem as corollaries. And for commutative rings and rigs, the condition is finitely generated projective. For quantales, you drop the finitely generated. Okay, so I was interested in Cauchy completeness or doing something on Cauchy completeness in honor of Bill Lawvere. And what I'm going to talk about today is, first of all, more examples for double categories, particularly locales, toposes, topological spaces, and quantales. And some of those examples are probably known. I don't think are in the literature, but not necessarily all of them. And then, well, the other thing I'll talk about, so there's really two parts to this. The other thing is I want to look at removing the commutativity from the 2017 theorem with Wood and relate it to well, for quantales, rings, and rigs, but also put into the theorem this condition about an SR bimodule having a right adjoint. So get it all in one theorem from this well in one corollary from this theorem of Wood. Okay, so let's see if it's advancing. Okay, so let me remind you, I hope people know what a double category is, but this will be a reminder. A double category D is a pseudo internal category in CAT. So unraveling that, you get that the objects X of D0 are called objects of D. This is just terminology. The morphisms F from X to Y of D0, I call them horizontal morphisms. Some people do it the other way and call them vertical, but they're the horizontal or tight, some people call them morphisms. The objects of D1, so here's D1, the objects of D1, X of S for source, X of T, T for target. So V, object of D1, is called a vertical morphism. Sometimes people call those loose morphisms. Okay, so the tight and loose people use because there are two ways to do this. The horizontal and the vertical can be either way. Okay, but this is the way I do it. Anyway, a morphism from V to W in D1 is called a cell of D. Okay. And one can talk about the vertical morphisms and what are called the special cells form a bicategory called, or denoted as vert D, the vertical category of D. Okay, vertical bicategory. And a cell is called special if both F0, Fs, and Ft, the horizontal morphisms in the cell, are identity morphisms. Okay, so a few examples that are relevant for this. Rel, the objects are sets, the morphisms are functions, the horizontal morphisms, the vertical morphisms are relations, and you have a cell from V to W if when X sub S, X sub T is in V, that implies that F of X sub S, F sub S of X sub S, F sub T of X sub T is in W. So that's rel. Another example of interest is cat. The objects are small categories. The horizontal morphisms are functors. The vertical morphisms are profunctors, also known as distributors or bimodules. And the cells are natural transformations from V to W with F sub S and F sub T substituted in. And then post, the objects are partially ordered sets. The morphisms are monotone or order preserving maps, the horizontal. The vertical morphisms are order ideals. And there is a cell precisely when it's the same as in rel, because an order ideal is a relation that's downward closed in one variable and upward closed in the other. And then finally, met, which is the double category of Lawvere metric spaces. And it's just VCAT, categories enriched in V, where V is that closed interval extended reals. So those are the examples initially of interest. There'll be some more later. Okay, so now we can talk about companions and conjoints. A companion for a horizontal morphism F is a vertical morphism F lower star equipped with cells of this form, eta and epsilon, whose horizontal and vertical compositions are identities. And I'll get to mention some examples later. A conjoint for F is a vertical morphism F upper star and cells, which I'm calling alpha and beta here, whose horizontal and vertical compositions are identities. And just a remark, rel, cat, post, and met have all companions and conjoints. Okay. So one can prove that if F has a companion and a conjoint, then F lower star is left adjoint to F upper star in the vertical bicategory of D. So that, I believe, is an exercise. Okay, and given that, one can define an object Y of a double category D to be Cauchy complete if every left adjoint vertical morphism V from X to Y is the companion of some F from X to Y, some horizontal morphism. So a little exercise, if someone's not seen this before, to get started on it, just good exercises to show that every set is Cauchy complete in rel. So the fact that a relation has a right adjoint is precisely says when you go through the properties that it's a function. And one remark, Cauchy completeness was considered in the 70s and 80s for metric spaces, categories, posets. And there's an article by Bourseau and Dejean, which gives an overview of what was known at that point and gives lots of examples. And it wasn't clear to me what was just expository and what was new in the article, but then I just spent a little time on it, skimming to see what they knew then, because I'm interested in something now. So where did my interest come? It's going to be, well, locales is one of them, but so a little over 10 years ago, I was interested in the fact that for locales, toposes, and topological spaces, I used something I had used in my PhD thesis for some of those, for I guess, no, right after my thesis in 81, I used Artin-Wraith gluing to construct locally exponentials of locally closed inclusions, because those are precisely the inclusions, the exponential objects in those three categories. And then in 2012, when I started getting interested in double categories, this is how I got interested, I was able to make a construction in double category I called the gluing category, where I could construct exponentials of locally closed inclusions with a single theorem for these three cases. So that's the interest in companions and conjoints. But as you'll see, it turns out one can look at Cauchy completeness here. Okay, so the double category of locales, the objects are locales. The horizontal morphisms are locale maps. So what are locale maps? They're order-preserving maps that have a finite meet, including the empty meet, which is the top, preserving left adjoint, which is traditionally denoted by F upper star. Okay. And then the vertical morphisms are these finite meet preserving maps. And the reason they were of interest is because those are precisely the things that you can do Artin-Wraith gluing with. And a cell is going the opposite direction that we saw in rel and post and cat, but for everything to work. And as you'll see in a second, what was considered in topos theory too was this direction. So there's a cell from V to W if F lower star followed by W followed by F lower star followed by W is less than or equal to V followed by F sub T lower star. Okay. So proposition you can prove is every locale is Cauchy complete in lock. So let's suppose V is left adjoint to W. So V is going from X to Y and W is going from Y to X. Then you know that VW is greater than or equal to the identity on the vertical identity on Y. And the vertical identity on X is greater than or equal to WV. So writing it, flipping the inequality so they're in the order, at least I'm used to seeing them, you see that W is a left adjoint to V instead of V being left adjoint to W, but W is left adjoint to V as poset maps. But since V preserves finite meets, it follows that, and has a left adjoint, it follows that V is a locale morphism, and, such that V lower star is V. Okay. Toposes. So in honor of the Topos Institute, no, this would have been there anyway. But toposes, you can take elementary toposes, you can take Grothendieck toposes, you can take toposes bounded over any base, anything. But I just said toposes. The horizontal morphisms are the geometric morphisms. The vertical morphisms are what are known as Lex exact or Lex functors. And Lex functor is a finite limit preserving functor. And so a geometric morphism, I'll remind you, has a left exact, left adjoint F upper star. Okay. And a cell in this category, there is these are the things that got glued in Artin-Wraith gluing. A cell is natural transformation from F lower star W into V followed by F sub T lower star. Okay, in that opposite direction. And then proposition is the same as for locales, essentially the same. Very little difference in the notation even. So suppose you have, every topos is Cauchy complete in whichever topos category you're looking at. So suppose V is left adjoint to W in topos. Then we have these cells, VW into the identity on Y and the identity on X. Sorry, the identity on VW, I have to read them the other way. The identity on Y into VW and the WV into the identity on X, satisfying the adjunction identities. That's what you get from the conditions on companion and conjoint. And so W is left adjoint to V as functors. But since V preserves finite limits is Lex by definition of this double category, it follows that V is a geometric morphism such that V lower star equals V in topos. Okay, topological spaces. This double category is lesser known, but I used it in the same way as I use for gluing construction. The locally closed inclusions are precisely the exponentiable ones, exponentiable inclusion morphisms. And that was back in my thesis. Those other two weren't, those came after. But so what's the double category of topological spaces? The objects are topological spaces. The horizontal morphisms are continuous morphisms. The vertical morphisms are the things you glue together in the gluing construction. So what's a vertical morphism from X sub S to X sub T is a left exact map from the open subsets of X sub S to the open subsets of X sub T. And left exact means finite intersection preserving, including the empty one, so including the top. And a cell, so I'm going to read this a little differently because we know that if you have a continuous map, that it's what's more recognizable as the inverse image. So if you have a map F sub S from X sub S to Y sub S, then if you have the inverse image in the other direction is just the inverse image. That's why it's called inverse image. So I'm going to read this the other way. So if you have W followed by F sub T inverse, that is contained in F sub S inverse followed by V. Okay. And that's just what you need to glue things together, an open and a close to get a space. Okay, so let's recall the definition of a sober space. Actually, it's not the definition. The property, a sober space is every irreducible closed subset is the closure of a unique point. But it's not important to note that that's the definition. That comes from algebraic geometry. But a space Y is called sober if and only if every morphism of locales from O of X into O of Y corresponds with precisely one continuous map F from X to Y. And there's a lot of ways to see this, but you can look at Johnstone stone spaces for that. Okay, so the proposition there is a space Y is Cauchy complete in top if and only if it's a sober space. Okay. So a left adjoint from X to Y in top. What is that? It's a left adjoint from O of X to O of Y in lock by definition of the vertical morphisms. So Y is Cauchy because precisely when it's sober, just by this property of characterizing sober spaces. Okay. Okay, next example, Quantales. Now, one can do commutative or not necessarily commutative, it doesn't really matter. So the category quant, the objects are Quantales, which are complete lattices with a a binary operation that distributes over suprema in both variables. And my quantales are unital. And the horizontal morphisms are locale homomorphisms, or locale morphisms. And what are they? They preserve all suprema. They preserve the multiplication and the unit of the quantale. And vertical morphisms, for me, in this case, there are a number of ways you can do quantales. We'll see another one later. But vertical morphisms are lax. So what is a lax functor? It's an order preserving map with the property that v of x times v of x prime is less than or equal to v of x prime for all x and x prime. And the unit e is less than or equal to v of the unit. And I didn't put subscripts on the unit because it got too messy with the x of s and the x of t. Okay, proposition, every quantile y is Cauchy complete in quant. Oh, by the way, the cells, let me just go back for 1 second. The cells notice are going the other way than the cells in locales, because a locale homomorphism is soup-preserving. It is a left adjoint, whereas in locales, a locale homomorphism is the in-preserving one, and you need the inequalities to go back the other way. Okay. So every quantile y is Cauchy complete in quant. And the proof is very similar to locales, but there's a little added thing. In fact, there are other examples, like the category of soup lattices. Every soup lattice is the same kind of thing. Every soup lattice is Cauchy complete in a category of soup lattices with order preserving maps of the verticals. Okay. Anyway, if you have V left adjoint to W in this double category of quantales, where V is going from X to Y, then since V is lax and preserves suits because it's a left adjoint, to see that it's a quantile morphism, it just suffices to show that V of E sub X is less than or equal to E sub Y, the other direction, and V of X prime is less than or equal to V of X times V of X prime. Okay, but E sub X is less than or equal to W of E sub X because W is lax. And then because you have an adjunction, you flip the V over and you get the V of E sub X is less than or equal to E sub Y. And also, because W is a right adjoint, you know that X is less than or equal to W V of X, and X prime is less than or equal to W V of X prime. So you get X prime is less than or equal to W V of X times W V of X prime. But because W is one of these lax, is a vertical morphism and is lax, we get W of V of X times, that's less than or equal to W of V of X times V of X prime, and that's precisely what we want. Okay, oh, not quite. You have to flip the W over using the adjunction. Okay, so Y is Cauchy complete in quant. Okay, next. So that was just the examples some of the examples that I'm aware of that weren't, at least as far as I know, in the literature before. So the other one I mentioned was the soup lattices, but you can also do, if you have a fixed quantile and you're interested in objects that are acted on by Q modules, objects acted on by a quantile Q, a similar thing happens. And it's a similar argument. The extra conditions you need are similar in proof to the ones down here. Okay. Okay. Oh, and by the way, one other thing. You didn't need to do anything extra for locales because you get one of the conditions for free because the operation is not just times, it's a meet. So you get an inequality, these inequalities down here for free. Okay. Okay, next, adjoints. This is the second part. Adjoints in double categories. So what we're working with is a bicomplete symmetric monoidal closed category. And we're going to consider the double category of monoids in V, not necessarily commutative. And I'm going to call that bimodule V or BIM V. The objects are monoids, pink rings, in V. And horizontal morphisms are monoid homomorphisms. A vertical morphism, now notice I have an R sub T, R sub S module going from R sub S to R sub T. You can do it either way. Some people do it one way and some people do it another. But in any case, if you're going from R sub S to R sub T, I'm assuming that's a right R sub S module and a left R sub T module. Okay. And I'm doing it that way because I was following what Paré did in his paper. In any case, a cell is, so if you have a homomorphism from R sub S to S sub S and a homomorphism from R sub T to S sub T, that makes N a bimodule from R sub S to R sub T, using F for the action on the F sub S for the action on the right and F sub T for the action on the left. Anyway, a cell is a homomorph, an R sub T, R sub S homomorphism from M to N. Okay, so that's a fairly standard double category of bimodules. Okay, let me remind you, given an SR bimodule M, there's a functor, and this is for any Q, any monoid Q, you get a functor from M tensor over R blank that goes from RQ modules into SQ modules. Okay, so basically, if you have an RQ module and tensor on the right, you get an SQ module. And that has a right adjoint, and I'm going to use this. This is pretty standard notation and well known, which I'll denote by S mod M blank. So if you take an SQ module and put it in there, you get an RQ module. It's a right Q module. Sorry, it's a right module because the thing you put in is right, and it becomes a left R module because it's contravariant in the first variable. Because M is a, where are we? M is a right R module that becomes a left R module. Okay. And it's well known that for commutative rings, M tensor over R blank has a left adjoint if and only if M is finitely generated and projective as an R module. And the work with Wood, we were just, in the commutative case, actually, the work with Wood was having a proof that we could then apply, a theorem we could then apply to rigs and Quantales. Okay. And by the way, I was interested in this for commutative rings because I was interested in, because tensor product is the coproduct of commutative rings. And the condition for a commutative ring to be co-exponentiable is precisely that as an R module, it's finitely generated and projective. Okay, so that's why I was interested in commutative case. I was aware that this held for bimodules over a single commutative ring back when I was interested in that and in my thesis. Okay, so now the question is, so the existence of this left adjoint to tensoring over R, can we relate that to right adjoints to the bimodule M from R to S? And then what about rigs and Quantales? And also, so in other words, can we put the two theorems together in one theorem? And the other thing is, what about the non-commutative case? Okay, and that can be done all at once. So one can prove the following theorem. I'm not going to go through the proof of this. I'll indicate how some of the parts work, but that's about it. So the theorem is the following are equivalent for a bimodule M from R to S, so it's an SR bimodule, which has a presentation. So if you think of it, for rings, which are monoids in abelian groups, every module has a presentation of this form. Similarly for rigs, which are monoids in the category of commutative monoids, and similarly for quantales, which are monoids in the category of sublattices. So in every case, you have a presentation. The only difference is for quantales, we don't need a finite presentation. It is true that, well, there are finiteness conditions that don't come in for quantales, but that won't be apparent because I'm not doing much of the proof. Okay, so the following are equivalent. M has a right adjoint in BIM V. The tensor product over S with M from QS mod into QR mod has a left adjoint for all Q. And tensor over S with M preserves limits for all Q also. And the fourth condition, which is the one that I believe was introduced in the paper with Wood, I don't know if it was hanging around earlier, but it is there's a canonical map that goes from S mod MS, tensor over S to M with M, into S mod MM, and that's invertible. Okay, so that's the fourth condition, and that was in the paper with Wood. So how does this proof go? You can prove B implies C implies D, just like we did in the 2017 paper. The only difference is we're not assuming, assuming bimodules instead of just modules, and we're not assuming commutativity here, but the proof goes through exactly the same. And then what you can do now is you can prove D implies A implies B. And that closes it up. Okay. And a corollary is the following are equivalent for an SR module M over quantales, and I'll get back to rings and rigs in a second. M has a right adjoint in the bimodule category. I would like to call that quantales, but I use quant for the one where the vertical morphisms are lax instead of modules. And tensoring over S with M has a left adjoint. And M is projective as an S module. Okay. And this theorem for quantales is in the Joyal-Tierney paper, but they're assuming their ring is commutative. I'm not saying they didn't know it for a non-commutative. Okay, so now if you look at for quantales, it's there. They're assuming their quantale is commutative. Now, if you look at rings and rigs, the only difference is that, and you don't really see it unless you write out the details of the proof, the only difference is that you have to add finitely generated projective. Okay. And the way the proof of this goes is you know that A implies B, and you know that A is equivalent to B, and you know that B is equivalent to D in the theorem. So what you do is you prove that D in the theorem holds if and only if this property C holds. In the case of quantales, just projective. In the case of rings, it's finitely generated projective. And where the finitely generated and projective comes in, etc., you use the inverse of this map theta. You look at the image of the identity under the inverse, and you're talking about a tensor product. So if you're in rings or rigs, it's a finite sum. If you're in quantales, it's a possibly infinite soup. So that's where the finitely generated comes out. And you use that sum that you get looking at the image of the identity to show the projectivity of the module. And parts of the proof use the presentation. Okay, and I'm hope I didn't go too fast because I finished a little earlier, but let me just mention what these papers. The first one is the Bourseau-Dijon paper, which was in the Cahiers in 1986, where you can find a lot of the earlier work on Cauchy complete categories, and he gives references for it and reproves some things. The next is, well, I just mentioned stone spaces because that's from 82, John Stone's book, because that's where you can find the, actually you can find it earlier in the Topos theory book, but his first Topos theory book, but that's where you can find the locale stuff. I think it's in there too, on sober spaces. And then Lawvere's original paper was in 73, but it was the first TAC reprint in 2002. And the paper with Wood, co-exponentiability and projectivity, Riggs, rings, and Quantales, was also in TAC. And then the earlier paper where the gluing came in, which is where my interest in companions and conjoints arose, was in JPAA. And finally, the recent Paré paper was in a book, a chapter in a book dedicated to or in memory of Lambach in 2021. Okay. So, any questions? And
All right. Thank you, Susan. Thank you so much for the talk and showing us all the different ways that Cauchy completeness can show up in different contexts. So now we'll go into the question section for our colloquium, and there are two ways you can ask questions in this colloquium. You could either raise your hand and then I'll call on you to unmute yourself, or you can type your question in the meeting chat. Because some people are not able to unmute themselves, so they can write their questions in the meeting chat, and I will ask on your behalf.
Can I make it so that I can see who's raising their hand? I don't seem to see.
Yeah, I think if you look at the
not that one.
I'm not sure if you can see it on your side. I could.
I think while I'm in full screen, I can't see it.
So I've made you a co-host, so you could technically see it if you want to. If you
I can scroll through. I can see. I just can't see everyone at once. That's
I see.
I can scroll through and see who's.
Okay. I can see the
hand,
hand, so I can call.
Okay.
I can call on them on your behalf.
Okay.
So I see Valeria. You've had your hand up. So Valeria, can you unmute yourself?
Oh, hello, Susan. How are you doing?
Good. How are you? It's been a long time.
It's true, long time. My question is about kind of the logical aspects of everything that you're talking about, because logic keeps showing up in funny ways, like the business that Paré book paper was in for Lambach. The fact that that quantales are in some ways about linear logic. And, even your old work is about exponentiability of objects, which is about kind of implications, looking at implications. So, what is the conclusion that you have after kind of generalizing it to double categories? Do you have anything to say about the logic of that? I'm sorry, it's a very open-ended question, I know.
Yeah, it's very open-handed. And I don't know, somebody else may know what kinds of logical things one can get from generalizing this all to double categories. For me, generalizing it in some sense, this might be a logical connection, but generalizing things to double categories, you can get single proofs that work for everything. And you also can get ideas of how to solve or how to state problems in other double categories when things look the same. So I don't know how much of a logical connection, a direct logical connection, but just the fact that topos theory can be involved. Yeah.
Sure.
And,
well, thank you. That's
a good question.
No, thank you. It's It's an interesting idea of kind of when we start generalizing, for it's something that in Topos we kind of discuss lots, is this business at the right level of abstraction, right? And
But,
cool.
in topos theory, by generalizing and using toposes, there are a lot of things you can do because you can do them in the internal logic. And then there are things that I was interested in that you suddenly can externalize and get properties for slices.
Slices, yeah.
And things like that.
That's fantastic. Thank you
Not
very much.
directly related to this. That's just.
Thank you.
Thank you. Thank you, Valeria, and thank you, Susan. So I see that Kevin, you have your hand up as well. You can unmute yourself and ask your question.
Sure. Hi, Susan. Thanks for the talk. I'm wondering about other characterizations of Cauchy completeness in a double category. So for me, in enriched category theory, the way I usually think about Cauchy completeness is in terms of V categories that have all absolute colimits. Yeah, which is very.
For me, split item points is just easier to say or think about.
Sure. Well, yeah, and then if you have a different enrichment base, sure. So, and you're working in double categories, which I think, if I didn't misunderstand, these double categories, like those of spaces and quantales, are equipment. So there's some theory of weighted colimits internal to them. Can we talk about absolute colimits for Cauchy completeness in these double categories?
That's a good question. One second. I'm jotting down what people's questions are. I don't know if anyone has done that. And it would be interesting to consider. I know that there's a lot done for V categories. Yeah. So what was known up to 86, you can find references in that Bourseau-de-Jean paper. But I don't know if there's a direct connection to these other examples.
Cool.
And I don't know if anyone's considered, I haven't thought about that because I think of these Cauchy complete categories as the ones for which idempotent split. And I think of it as more in an algebraic sort of way than
Yeah. Fun, weird brain teaser anyway to think about, I guess, a colimit of a geometric morphism weighted by a Lex functor or something. Maybe there's something fun there.
But Lax colimits are where that's what the gluing construction is, a Lax colimit. The Artin-Wraith gluing came up as a special case of Lax colimits. So you're asking about all these, is there something general in double categories that would give that, right? Well, I mean, I suppose, there's the generalization to double categories or abstraction to double categories of the Grothendieck of the Artin-Wraith gluing is a cotabulator. So it's called a cotabulator.
I think I'm thinking of a level shift of that, though, rather than a colimit in the double category as a whole, right? That the cotabulator would be, but a colimit in an object of the double category, right? You can talk about limits and colimits of a tight morphism weighted by a loose morphism. So that would be like, I have a geometric morphism and I have a Lex functor out of the domain, right? And I somehow try to construct a new geometric morphism out of the codomain and that, like, anyway, this also might not really do anything in these cases, but I was just wondering.
That'd be interesting. Yes.
Yeah. Thanks.
Great. Thank you, Kevin and Susan. We have 3 hands. I think Evan was first, and then David and Nathaniel. So maybe Evan, you can unmute yourself.
Great, thanks. Yeah, thanks for the talk. That was really interesting. So I noticed that when you alluded to this briefly, when you set up your double category of quantales originally, you had the lax maps as the loose arrows. And I think if you apply the bimodule construction to soup lattices, you get a different notion of loose map. And so I'm just sort of wondering how those fit together and why you chose one in the first case, and what sort of the connection is between these different double categories. It's certainly often been my experience that there are lots of different ways to configure the loose morphism, and it's not always obvious what one should do. So
in particular for Quantales, there's modules, the bimodules also.
Yeah.
Those are completely different kinds of things. Okay, so the reason that I was interested in the lax morphisms really had to do with I was interested in cotabulators in those categories because I wanted to do gluing kinds of things. But with modules over a quantile, those lax morphisms, well, the lax morphisms you would want would be they were lax via the multiplication, so the soup preserving maps. If you have two soup lattices which Q acts on, so Q modules, and a lax morphism between them, you would have a soup preserving map, which is for which the action is lax. Okay, so an AF of X is less than or equal to F of AX, that kind of thing. And those maps came up in a whole other context that I was interested. I mentioned them now. I didn't put that example in here, but they basically were, I don't remember all the details offhand, but they came up in another context where ones with right adjoints were the kinds of, or with adjoints were the kinds of homomorphisms we were interested in.
Yeah, so basically just, different
I
ones
remember
for
what
different.
it was. So, I don't know if this is relevant, but that there's a characterization of completely distributive lattices that has to do with tensoring with a soup lattice having a left adjoint. Is that where it comes out? Yeah, I believe it's there, but there's a property where completely distributive lattices come in. And I was interested in basically in the same thing for Q algebras. And that's where these objects I call Q posets came in. And you could do the same kind of thing there. Q posets or Q soup lattices, things like that were coming up in that context. They're actually what I would just call Q soup lattices with an action of Q. But in the context that it came up, it was, I don't know if this makes sense, but it was trying to generalize the construction of the down set soup lattice in the case when you're not just talking about a soup lattice, but you wanted it for a soup lattice with an action. So that's where that came up.
Okay, yeah, thanks for the context. Yeah.
Great. Thank you, Evan. And David, I believe you have a question.
Yeah, thanks for the talk, Susan. That's great. You were talking about this condition of presentation. Is that happening locally between, you're looking at like this co-equalizer in a local
yes, in the
or maybe local vertical. Sorry, I usually do think in the local vertical category.
Yeah, I mean, that every module is
that's where it's showing up. And you need, and what can you say, and that, can you say anything about like the proof or like how that relates to projectivity, or what you're
go up there we go. There's two. How that relates to projectivity.
Oh no, sorry.
Where that comes up is
where that comes up here,
in proving that this morphism theta is invertible. You put the presentation in the first variable of the HOMs. Okay, and the soups come out as products, and here and here. Okay, and basically what happens is using the fact that and you have co-equalizers, so and the co-equalizers turn into equalizers. So using the fact that condition C says that tensoring preserves limits, you
Mhm.
get that one of the co-equalizers. One thing here is a co-equalizer. This thing always takes co-equalizers to equalizers, and basically you get isomorphisms over here. And so, sorry, you get isomorphisms. I'm making my co-equalizers go down in equalizers.
Mhm.
You get isomorphisms down here, and chasing your diagram, and you get basically chasing your diagram, you see that this thing is an isomorphism. So that's how it comes up. The fact that these functors, when you let M vary, that they take co-limits to limits. So if tensoring with M preserves limits, then you get things falling out.
Great. Okay,
Does that
thanks.
make sense?
Yeah,
I mean, that's the original proof. And there was one other, did it come up one other place? I'm trying to remember. I mean, I wrote it all out, I'm in the process of writing it out, all out for the volume in honor of Lawvere. And so I rechecked, I'm putting all the conditions in. I'm not just saying see, because it's the commutativity is gone. I'm not just saying see the paper with Wood.
Mhm. Right. The tensor is still symmetric, but you're not looking at commutative objects.
Yeah, because
yeah.
It's,
okay, thanks.
tensor is only symmetric in V.
Mhm. Yeah.
It's not symmetric in the module categories because you have two different sides.
Right. Yeah. Okay, thanks.
You're welcome.
Thanks, David. Thanks, Susan. And Nathaniel, I believe you have a question. You can unmute yourself.
Hi.
Hello, thank you very much for the talk. It's very interesting. I had, well, two very related questions. So I'll ask them as one question together. So the first one was about the assumptions on V. I was wondering, are things like symmetry and closure really necessary to prove your main theorem? Does it hold a more generality, or is there really an essential use of symmetry, for instance, in this result?
The actual theorem, I don't believe I used symmetry. I don't see where you would, because it's, in the theorem, there's tensoring over S. Right? So I'm trying to show that again. Can you see, when I'm looking at, I wanted to see Nathan who was talking. Can you see my assumptions?
Yeah.
Oh, you can. When you're there, okay. I can go back and see. In any case, I don't think, I'm not going to bother to go back, but I don't think that symmetry comes in. The reason that I put it in there basically is because of the applications to Quantales rings and rigs.
I see.
Because there's symmetry in V there. But I also don't know. Let me see if I can, it's not letting me go back there. Let me see if I can get back.
I suppose the reason I ask is because I'm interested in various situations in which you don't have symmetry on some monoidal category, and so.
Which ones what are you interested in?
Well, I think things like functor categories, for instance, with various monoidal structures as one class of examples, but also more generally bicategory enrichment, which tends to work similarly to non-symmetric monoidal enrichment. So I had another very related question, so hopefully I can sneak that one in too. So at the moment you're considering the monoids in V and the bimodules. So I was wondering whether you considered the sort of multi-object case and looking at V categories and V profunctors, so that double category, and whether you have a similar theorem as on the slide at the moment.
Well,
in this setting.
Yeah, I think that a lot of the activity in the 70s and 80s was for V categories. So there was a lot done there. So I am not replicating that. So are you asking whether you could do that in the context of one of these general?
I'm asking whether, if on the previous slide you replace bimod V with V prof, whether you have you can prove something similar about the adjoints being equivalent to preservation of limits and this invertibility condition.
Yeah, okay. So so when I look back at what was known or what was generalized from just cap to VCap, I didn't look at it in that much detail. There are a lot of theorems so there's a number of properties. As I mentioned, there's the idempotent split, there's the absolute colimit property. There's some theorems which you can find there's some in Walter's work, Street's work. Those references are in the Bourseau paper. And I don't remember when I was looking back, at that point, I wasn't really I was just thinking about honoring Bill with the many examples that things kept coming up that were like Cauchy completeness. And so when I got to this preservation of limits, I didn't look back. So I don't know. That might be an interesting thing to look at, whether all those theorems can be done in a similar way. But thank you.
Thank you very much.
Thank you so much, Nathaniel. Thank you, Susan. I think we are going to end the live stream on YouTube now, and then we will continue our discussions on Zoom. So thank you for all our viewers on YouTube.
Now, maybe